explicit in the sense that I've been encountering questions in studying supersymmetric gauge theories, which are related to chiral algebras. And although some of the questions I could address with my limited knowledge of chiral algebras or with the help of various collaborators, I think there are some very general problems that deserve to be looked at and in a systematic way. And so this is in this talk, I'm going to sort of point to questions which I do not know how to answer and that I would love to learn how to answer. So my wish list is for people in the audience to tell me things after the talk or over the next few meetings. So this work is based on papers written with various collaborators, including Thomas Kretzi and Costello and Tudor. And the general theme is that of vertex algebras which emerge in gauge theory calculations. And the prototypical example of this is what happens in Chern-Simons theory, and many in the audience are presumably familiar with this. So in Chern-Simons theory is a quantum field theory in 3 dimensions, labeled by a choice of semi-simple gauge group G and of some level, which is a pairing with some integrality properties on the algebra. And it's a theory that quantizes quantizes flat connections. So you start from a classical theory with solutions are flat connections on your 3 manifolds, and you study quantum field theory based on that. And the action, there is some schematic action, which is in a way ADA plus A cubed. And the main property of this action is that it's topological, meaning that you can write it down without any reference to a metric. And so that means that the quantum field theory you produce like that, up to some subtleties which appear in quantization, is itself topological. So calculations can be done in principle, without reference to a metric. You can change your metric without changing the answers, and you can essentially move or deform the position of the shape of your manifold or the position of operators continuously without changing the answers, unless you do something singular. So this is a prototypical example of a topological field theory, and is used in physics in a variety of situations where you have quantum field theories which have sort of no local degrees of freedom. Being a physical quantum field theory, it has also this property of unitarity, which in practice implies a variety of semi-simplicity constraints on the pieces of the theory. And topological invariance plus unitarity are very strong constraints. For example, they essentially tell you that the theory is not going to have any local operators, except for the identity operator. And which means that the sort of the standard questions we can ask to quantum field theory, like what is a correlation function of a bunch of operators on the plane, say on a flat space, are not going to be interesting for Chern-Simons theory. In order to, so if you just use standard ingredients, the basic question you can ask from Chern-Simons theory is pretty much the partition function on a 3 manifold with some non-trivial shape. So you get a 3 manifold invariant. You can get more information if you add defects which are extended along. So if you add not just local operators, but what are called extended defects, which are sort of modifications of the theory along some submanifolds. The canonical example in Chern-Simons theory are Wilson lines. A Wilson line defect is essentially the quantization of the notion of holonomy of a flat connection. And so you can consider now the partition function or correlation function of Chern-Simons theory on a 3 manifold in the presence of a collection of lines labeled by some data, which are roughly a representation of the group. This is celebrated to give. This is a celebrated way to give us things like knot invariants. And these Wilson lines are also topological, can be sort of deformed, fused, braided around each other. And all of this sort of data is collected in something called the modular tensor category. So there is a braided, in general, lines in 3D, in a three-dimensional topological theory, would give us a braided tensor category. And then these sort of simplicity conditions that come from unitarity tell us that we have only a finite collection of lines, and they have no log, they are all simple, and so on and so forth. And you get this sort of modular tensor category. And this is sort of the basic topological data of the theory. You can enrich the problem by adding more complicated defects. So we said there are no local operators, which are point-like defects. There are line defects. And you can consider also surface defects, which are essentially either interfaces or boundaries for your three-dimensional manifold where the quantum field theory lives. It actually turns out that in the Simens theories, it's actually quite rare to find topological boundary conditions, though you can find some. But it's very common to be able to define what are called holomorphic boundary conditions, which mean boundary conditions which require you to specify a complex structure along the boundary. So they don't require you a metric, the full content of a metric, but a little piece of it, which is this complex structure. As a consequence, objects that live at the boundary are not topological anymore. For example, local operators that live at the boundary will have an holomorphic dependence on their position. A correlation function that has one of such boundaries will depend holomorphically on the position of local operators at the boundary. And in particular, if you sort of follow the axioms of quantum field theory, this implies that the boundary operators form a vertex operator algebra. And the canonical example that comes from a very specific boundary condition is the WZW vertex algebra, which arises at Dirichlet boundary conditions in this Simens theory. So these holomorphic boundary conditions have a variety of interplay with the other ingredients of your theory. For example, you can consider topological lines that end at the boundary, and you can argue that you'll find modules for the vertex algebra living at the endpoints of this line. Now, vertex algebra, the WCW vertex algebra is the basic example of a rational conformal field theory. It has a nice category of modules, which is a modular tensor category, and the physics is sort of telling you that whatever is the modular tensor category of your bulk lines will have a map into the modular tensor category of the modules for this boundary vertex algebra. You can get a very large variety of rational conformal field theories by just playing around with boundary conditions and interfaces for Simens theory. For example, you can study Milman models as living in a holomorphic interface between multiple Simens H theories. In general, the whole theory of rational conformal field theories is pretty much formulated in a way that is closely connected to the topological field theories. And I would like to explain a bit better how what are the implications for a vertex algebra to be living at the boundary of a three-dimensional topological field theory. So let me draw a few pictures and discuss their meaning. So I want to use the gauge theory to produce some correlation functions which have a meaning in the chiral algebra. So the simplest thing I can do is to take the three-dimensional topological field theory on R plus times the Riemann surface and place the boundary condition at the origin of R plus, which means I have a picture like this. Can you see my mouse on the?
Yes.
Okay. And it's full screen, right?
It is. If you, it would actually help if you made it a little bigger,
Sorry,
That's
I should have left this better now.
Yeah, that's perfect.
Yeah, my problem is that my mouse then disappears for some reason, that because some strange interaction between Zoom and the software I'm using.
I have my mouse. I can point if you tell me where.
So you cannot see my mouse, correct? Okay,
No,
that's
I
fine.
can't see.
So on the picture on the left, on the boundary, you can place some collection of elements of your vertex algebra, of all of these fields, of these boundary fields. And you can compute the correlation function on this geometry. Because the geometry has a non-compact direction, you need to also specify a state for the two-dimensional topological field theory, which will be placed to the very left. And then you should be able to just get an answer, a correlation function, a number. And this number will vary homomorphically as you vary the position of the local operators at the boundary. So these correlation functions are meromorphic functions of the positions, because the vertex these vertex operators, these local operators, can have a singular OPE, operator product expansion, when they come close to each other. But the poles of these correlation functions are completely controlled by the vertex algebra structure. And so this correlation function is what would be called mathematically a conformal block, or an element of the chiral cohomology, so it was another name that I was going to use, but I forget now. So essentially, this picture is telling you that there is a map from the space of states of the topological field theory to the space of conformal blocks of the chiral algebra. And both sides of this correspondence have a very specific behavior as you deform your Riemann surface. The conformal block of a chiral algebra satisfies KZ equations, or anyway equations that tell you how the conformal block varies. They define flat connection in the space of complex structure of the Riemann surface, and then this flat connection can be integrated to get an action of the mapping class group on the space of conformal blocks. And the space of states of the topological field theory is also locally constant as you deform your surface, but has monodromies if you apply mapping class group transformations. So the fact that the vertex algebra lives at the boundary of topological field theory tells you that the topological field theory gives information about the conformal blocks of the vertex algebra. Possibly in the presence of non-trivial modules, if you have lines which end at the boundary. So this is one kind of piece of information that you get from the fact that you have a topological field theory interpretation here. Now, in the Simens unitary situation, typically these maps are isomorphisms, so that the space of states of the topological field theory is just the same as the space of conformal blocks of the boundary vertex algebra. This is not obviously the case in the situation I'm going to discuss later on, so I'm not stressing this point. For now, you just have, the pictures will just tell you at first sight that you have functors from lines to modules, and maps from states to conformal blocks. And these maps can be sort of inverted in the sense that if you give me an abstract rational conformal field theory, I can build an abstract topological field theory such that the conformal field theory lives at its boundary. So this topological field theory will be given in completely abstract terms, in terms of the modular tensor category of modules of the rational conformal field theory. And so it's sort of a very strongly coupled abstract description, is not a gauge theory description. You might rightfully ask, what do you gain by actually having a Simens description of this system instead of an abstract topological field theory picture? And in practice, it means that if you want, you could compute a variety of things in gauge theory. For example, the WCW model that I mentioned has the property that the vacuum module can be described as the cohomology of some line bundle on the affine Grassmannian, or that the space of conformal blocks is the cohomology of some line bundle on band G. These sort of statements are at the core gauge theory statements. And so I just wanted to sort of stress this point that there is a bit of a difference between saying, okay, this rational conformal field theory lives at the boundary of topological field theory abstractly, or saying, no, it lives at the boundary of a very specific topological field theory for which I have a Lagrangian description and I can try to do calculations, maybe perturbatively, maybe non-perturbatively, but it sort of gives an independent way to do calculations with this conformal field theory. Now, for rational conformal field theories, we know everything pretty much. So the gauge theory perspective, I'm not sure how much you gain from the gauge theory perspective, although the mathematical statements are presumably interesting still. But when we move on to more general situations, I hope that the gauge theory perspective really gives novel insights on the properties of the boundary vertex algebras. Now, there is another type of constructions you can do. So at the moment I introduced topological lines, I introduced holomorphic boundaries. There are also other things that you can put in the theory. There are topological boundary conditions, as I mentioned sometimes. And there are often topological interfaces between multiple topological theories. And you can also have anti-holomorphic boundary conditions. So boundary conditions where the chiral algebra is, where you have an anti-chiral algebra instead of a chiral algebra. And you can draw pictures in the three-dimensional topological field theory which produce interesting structures out of these basic ingredients. For example, these sort of sandwiches between an holomorphic and an anti-holomorphic boundary condition that I depicted on the right end up giving you things like modular invariant partition functions or just definitions of two-dimensional conformal field theories, which have a given chiral algebra on the holomorphic side and a given chiral algebra on the anti-holomorphic side. And indeed, the whole theory of rational conformal field theory is just an explicit or painfully implicit way to make sense of these sort of pictures. And right, so you can make statements like, I don't know, a topological boundary condition will give you a very special conformal block, which is independent of the under the action of the invariant and action mapping class group. Or it will allow you to give an extent, to find a modular extension of your chiral algebra. So there is a variety of conformal field theory statements, of rational vertex algebra statements, which can be encoded in statements about various defects in the three-dimensional, in the associated three-dimensional theory. Okay, so this is the sort of the rational the rational world where everything is unitary, semi-simple, and very nice. Today, I would like to discuss situations where you relax this constraint a little bit. In particular, you don't impose unitarity anymore, and where topological invariance is imposed not sort of on the nose, but through a BRST procedure, so that you have a cohomological topological field theory. So the differential graded version of the pictures I was drawing in the previous slides. And the natural setup where these sort of things emerge was discussed in Tudor's talk first in this meeting, and it's the topological twist of three-dimensional gauge theories. Three-dimensional gauge theory is equal for supersymmetry. So if you have a three-dimensional gauge theory with n equal for supersymmetry, it has these two twists, A and B twists, that give you topological field theories in 3 dimensions. And these are differential graded topological field theories. And you might ask, what can you do with them? How many of the pictures we drew in the previous slides can apply to these theories? How do these theories look like? The B twist is very similar to Chern-Simons theory. it's essentially a Chern-Simons theory for complicated supergroup, which is built out of the algebra G of your gauge group, its dual, and fermionic generators associated to the matter. So you remember from several of the previous talks, the simplest three-dimensional equal true gauge theories are labeled by a group and a synthetic representation M. And we can use these ingredients to make the super Lie algebra. And the B twist is a Chern-Simons theory for the super Lie algebra. Incidentally, looking at Tudor's talk again, I was reminded of the fact, so there is a variant to this construction where you turn on Chern-Simons couplings for some of the gauge groups. And this requires some very specific constraint to the moment maps to the matter fields. And I expect that this is essentially, I mean, I've not seen done. It would be nice to present this combined system again as a Chern-Simons theory. I think it's very doable. I assume that the constraint of the moment maps is just required so that the resulting Lie algebra satisfies Jacobi identities. At least this is what happened in similar situations. The A twist is a little bit harder to describe. I'm not gonna say much here, but like, I mean, Tudor was mentioning, this is kind of like a dimensional reduction of Seiberg-Witten theory or Donaldson-Witten theory. Another way you can think about it is that it's built to control the analytic continuation of, it's sort of the most natural thing you could do to study the chiral algebra of symplectic bosons or gauged symplectic bosons. So I'll get back to that. Anyway, one of the consequences of not being unitary is that these theories admit local operators. They have a nice infinite-dimensional space of local operators, which is what you'd say that the theory attaches to a sphere. And these local operators form a Poisson algebra, and it's typically the algebra of holomorphic functions on what are called the Higgs and Coulomb branches of the theory. So depending if you do the A or B twist, you find holomorphic functions on M or G, or on the BFN Coulomb or generalizations Coulomb branch for the gauge theory. Are there any questions? Sorry, I went almost half an hour without questions. Okay.
I have a stupid question. So you said that you can add the Chern-Simons term to, I mean, the Chern-Simons has to do with the B twist, but then somehow, if you believe in 3D mirror symmetry, then something analogous should exist for the A twist as well. And what would it like? What is the 3D mirror of the Chern-Simons of adding the Chern-Simons term?
So you can try to give answers to this question using four-dimensional gauge theory. So suppose that you have some theory and you want to gauge G with the level K. You can sort of make this into a sandwich where you have the theory living at the boundary of four-dimensional gauge theory, and then a certain modification of Neumann boundary conditions on the right-hand side, which has this Chern-Simons level included. Now, in order to do mirror symmetry, we want to apply S-duality to this whole picture. Now, you know how to apply S-duality to the side with the matter fields. So what the new ingredient you need is to figure out how to apply S-duality to this modified Neumann boundary condition. And the outcome of this S-duality on the modified Neumann is, well, it's a complicated thing, potentially, but it's essentially what Tudor was calling T of N and K. So you could try to build a mirror by taking the S-dual of the boundary condition, taking T of N and K, engaging the diagonal G-dual symmetry.
Yes, but somehow you said that you have this Chern-Simons term only if the moment map satisfies some constraint. So how will we see it on the other side? Okay,
so I understand now the question, sorry. I do not know. I just do not know. So I do not know how this Chern-Simons coupling would affect the chiral algebra or the sympathetic bosons. I just do not know. I have not thought about it. I should stress that there are things that could be done possibly in the topological theory which cannot be done in the physical theory. So this constraint on the moment maps is required to have 3D unequal force supersymmetry. Now, is it required in the topologically twisted theory? That I don't know.
The Chern-Simons is an n=2 gauging, and I think it sort of makes sense. I mean, you just have to gauge the right sort of symmetry, and either the A twist or the B twist. And in terms of the chiral algebra, you would expect an external Kac-Moody action that you just want to gauge at level K.
It's not so that you can do things at a 3D unequal true level for sure, but are they compatible with the A and B twist? That's not clear. So you can definitely have a setup in the homomorphic topological twist, and then it can survive A and B twist only if it preserves these extra supercharges that are present in the holomorphic twist. And it's a calculation to see if the boundary condition does preserve it. And it's a calculation that depends on the boundary condition. So I should not absolutely give you the impression that there is a unique holomorphic boundary condition. So even in the pictures I was drawing before, right, a given three-dimensional topological field theory can have a vast collection of holomorphic boundary conditions in principle. Even Chern-Simons theory has the WZW boundary condition. It also has other boundary conditions. And once you relax unitarity, there is even a greater variability of things you can do. And some of them might. It's possible that only some of them are compatible with gauging a Chern-Simons, adding a Chern-Simons group. I don't know. This would have really to be looked at carefully. So I'm not gonna try to make a precise statement here but I think it would be high time to figure these things out. I mean, I think we should be at a place where you could do the analog of BFN in the presence of a Chern-Simons coupling. I should say that these sort of Chern-Simons and equal 4-gauge theories are not just obtained by turning on a Chern-Simons coupling in the gauge theory. Because there is no way to write down both a Yang-Mills and a Chern-Simons action with an equal 4 supersymmetry. So you're really just turning on a Chern-Simons coupling. And I wonder how this affects a variety of calculations. I don't know. Anyway, so this is definitely an interesting project, but not something immediate, I think. But I think trying to enrich the Chern-Simons supergroup that arises in the B twist will be a natural starting point. So, right. So, as I anticipated, these topologically twisted 3D unequal 4-gauge theories do admit holomorphic boundary conditions. So they are built in a bit of a bizarre way. So you start with a physical boundary condition that preserves 0,4 supersymmetry. That's compatible with an holomorphic topological twist, but not with the topological twists. Then you deform it to make it compatible with the topological twist. This deformation is not always available. we pretty much just found examples where things work, but there might be more examples. Again, we did not do things as systematically as one might want. On the B side, there is a boundary condition which is essentially the analog of WCW in Simons theory. And so we expect the vertex algebra to be the WCW model for this supergroup, this G plus fermionic M plus G2. What is the WCW model in practice? I don't know. Has not been computed in almost any examples. It should be defined, the vacuum model should be defined as the cohomology of some line bundle in the fine Grassmannian for this super Lie group. But first element of my wish list, I wish somebody would compute some of these WCW models for nice gauge theories. Because it is sort of a precondition to do a lot of calculations. There are variants of the WCW construction. You can also get Drinfeld-Sokolov reduction, so this WCW sigma model, WCW model, whatever that is. I mean, intuitively, I expect it to be maybe an extension of a quotient of the Kasmoudi algebra from this for this supergroup, but the details are unclear. On the A side, the setup produces very naturally a vertex algebra which we can call a gauge symplectic boson. More precisely, whenever you have a symplectic vector space M, you can associate to it a beta gamma system, so that beta and gamma together are valued inside M. This will have, if M has a symplectic G action, then these symplectic bosons will have a Kasmoudi algebra for G, which will have some negative level, which depends on M, on the Casimir of M. You can, if this level is sufficiently negative, you can add extra fermions transforming under G to bring it to be equal to minus twice the critical level. And once it's twice the critical level, you can gauge the G symmetry, and there will be a Resti reduction by G. And you're left with some new vertex algebra. And this is what you find at the boundary of the A-twisted theories. So you need to, and there is a bit of freedom here. There might be different choices of V that cancel the gauge anomaly. So these are the simplest possibilities. Then Tudor discussed a very nice example which involves extra Chern-Simons couplings. There are also other examples that are non-Lagrangian in a sense, and that reproduce some vertex algebras introduced by Arakawa some time ago in the context of class S theories. But they can also be found as boundary theories for some 3D theories. And maybe I'll discuss a little bit at the end of the talk. And in general, I expect that a very large collection of interesting, not quite rational logarithmic vertex algebras might be found at the boundary of these topologically twisted 3D gauge theories. And then, if that's the case, in all of these examples, you should be able to think about pictures like this. So find relationships between space of states and conformal blocks, line defects and modules, and perhaps discuss the analog of modular invariants for these logarithmic VOAs, or modular extensions or whatnot, just by looking at the appropriate objects in the twisted gauge theory. Any questions? So I don't have very many examples to discuss, because most of the things have not been computed yet. I have a variety of guesses, but I'm not sure how I used to do that. And some of the examples get a bit intricate. But I can try to discuss the simplest example of mirror symmetry, which is the relationship between a Yuan gauge theory coupled to one hypermultiplet, meaning the representation is C2. Yes?
Yeah, we're good.
And C2 without any gauge group. So this is a basic example of three-dimensional mirror symmetry. The A twist of one theory should be the same as the B twist of the other, and vice versa. And we can try to compute and compare the vertex algebras on the two sides with the caution that it's not clear that the two will have to be the same, because who knows if the boundary conditions we're looking at are themselves mirror. But it seems that we got lucky. So let's do the B twist of this U1 theory. It's going to be a Chern-Simons theory based on some supergroup which has two bosonic generators and two fermionic generators. And it turns out to be U1/1 at level 1. And so we need to figure out what is the WCW model for U1/1 at level 1. And the reason, so it's quite clear that this is probably going to be something interesting, because if I just look at U1 at level 1, for example, that gives you free fermions. So the Kasmoudi algebra, of course, is just a current, but the WCW model is more than the current. It has a whole set of free fermions. If you do on the mirror side, we expect to find just symplectic bosons corresponding to this C2. And what actually seemed to be the case, but is that this WCW model for U1/1 is secretly just the product of a pair of symplectic fermions, pair of symplectic bosons, and some free fermions. So the vertex algebras are not the same, but they differ just by some free fermions, which do not affect conformal blocks, do not affect the category of modules, or things like that. So this is compatible with mirror symmetry. But it's a non-trivial calculation. I mean, I do not know for a fact that U1/1 level 1 WCW model should be the product of symplectic bosons and free fermions. It's plausible because the right-hand side has Kasmoudi currents at level 1, but I don't know if the actual calculation of whatever cohomology on the fine Grassmannia would give this answer. If you do the A twist, on the left-hand side, you need to gauge symplectic bosons. These symplectic bosons have a U1 Kasmoudi current at level -1. To gauge U1, I need to have level 0, so I can add free fermions at level 1, which have level 1 current, and do the quotient. So I have a symplectic bosons times free fermions modulo U1. It's a nice BRST reduction. You can more or less do it. And what you're left with is just two fermionic currents, which is what you expect from the B twist of the mirror theory. So that's nice. So this is pretty much the only example where I can match things. I thought one should be able to get a lot more abelian mirror pairs just by staring at it, taking multiple copies of this example and thinking deeply enough about gauging or engaging U1s. But again, has not been done. If you look at non-abelian mirror pairs, you do get vertex algebras which look quite different from each other. And again, I don't know if they can be related by some simple construction or if they just happen to be vertex algebras which have the same category of modules in the same space of conformal blocks and yet are completely different. Again, I would love to work out some examples and understand what's going on. So definitely big wish list. Figure out what are the WCW models for these super Lie algebras. Any question? So, in order to discuss things further, we need to know things about things like topological lines in these gauge theories, or topological boundary conditions in these gauge theories. And mathematically, this is a subject which is just being addressed at the moment. For example, Justin Hilburn and collaborators have been doing beautiful work trying to figure out what are the possible line defects or boundary conditions for these gauge theories. And there is a lot of intricate algebraic geometry involved. But in principle, I expect to see some braided differential graded category of line defects and some functor into a braided differential graded category of modules for these logarithmic UAs. And on both sides, there is a, the difficult question is which do I keep, right? In a sense, there are, the collection of all possible modules for UA is huge. It's not quite clear which ones will be physical, realizable in the physical theory. For example, do I need to have them, I don't know, do I have should the stress tensor eigenvalues, should they be bounded somehow in terms of the eigenvalues L0 of L0 or the modes of the Virasoro algebra, or should the highest weights of Virasoro or not? I don't think has been fully established. What should one put on the left? What should I put on the right to get a nice map? But it doesn't have to be an equivalence, as far as I know. You only need a functor. So maybe so right. So as I said, it is not clear that one should get equivalences in this situation. So perhaps one should just be relax a little bit and work with functors, and then you don't have to worry too much that these are not subjective or not injective or whatnot. Now, the very basic calculation you can do to check these statements is to take the simplest module, which is the vacuum module, and compare the endomorphisms to the vacuum module on the two sides. So on the left-hand side, we should have the holomorphic functions in the Higgs branch or Coulomb branch. On the right-hand side, we need to have some kind of derived endomorphisms to the vacuum module. And in the work with Costello and Herzig, we did some checks by hand that for the A-twist, things seem to be working examples, but we don't. And looking at looking at Braverman's talk at this conference, where the Weil algebra of M of K appears, makes me hopeful that perhaps things can be set up in such a way that the construction automatically matches endomorphisms of the vacuum module with the BFN Coulomb branch or the generalization to general N. On the A side, sorry, on the B side.
Can I ask you a question?
Yes.
It's on the first line of this slide. So before you had a map from line defects to conformal blocks.
No, to modules. And then there is a map from states to conformal blocks.
Oh, so the full states of the TFT to conformal blocks. Okay, yes. So when you move to DG TQFTs, I would have expected a DG version of conformal blocks, not
yes, absolutely,
category of modules.
Absolutely, that's correct. So I would expect to have the states, which are derived a complex map, some differential graded conformal blocks.
Okay, so this is not in contradiction. I thought at some point you're identifying conformal blocks with something about modules, which is something only true in genus 1, and this is not happening.
No. I never do that.
Okay.
So, right. So you have the DG category of line defects, which will map with a functor to the DG category of modules, and you have states which map to conformal blocks. And the space of states depend on which line defects you put at various points on the surface. And similarly, conformal blocks depend on which modules you have placed on the surface.
That's right. Thanks.
And the spaces of states or of conformal blocks are intricate, complicated, interesting. Even in the simplest examples, if I look at symplectic bosons as a function of the bundle you put on the surface, the space of conformal blocks jumps in interesting ways. It has components in various cohomological degree, and so does the space of states, I guess. So so the derived aspect of this correspondence is definitely important. Now, again, as I don't know what WCW model is for the supergroup algebra, I cannot show that that the endomorphisms of the vacuum module are the same as M modulo G, but it seems not crazy. I mean, if you don't have a gauge group, then Tudor was explaining this. Like he was saying, you know, if I take the vertex algebra of currents, of fermionic currents valued in M, the endomorphisms of the vacuum module are some polynomial algebra and some odd generators, and then you can Poisson dualize it to polynomial algebra and Poissonic generators and reproduce M itself. The gauge version of the statement should also hold. The proof, I don't know. I don't know how the proof works exactly. But it would be nice to get it. Nice. And to extend it to non-trivial modules, of course. In these calculations I did by hand with Costello and Kerzi, the basic trick was that if you look at symplectic bosons, there are a variety of modules. There is the vacuum module, and there are modules obtained by spectral flow of the vacuum module, which pretty much means that you are taking some generators in this Weil algebra of M of k, and you are taking highest weight instead of lowest weight modules for some of these Weil algebras. And then there are, just looking at Weil algebras, you can find extensions of modules, things that map the vacuum module to extend the vacuum module by some spectral flow image of the vacuum module. And then when you gauge the symmetry, it turns out that many of these spectral flow modules end up giving you the same vacuum module of the gauged vertex algebra. And so we argue that you can inherit endomorphisms of the vacuum module from extensions of the vacuum module by spectral flow modules in the synthetic boson vertex algebra, which I think was a cute construction that it's worth exploring further. Another important ingredient, I think, for this for developing these ideas is to look at topological boundary conditions. So it turns out that these twisted gauge theories have a ton of topological boundary conditions, which come from Chukumachu boundary conditions of the original physical theory. These boundary conditions play a role in a variety of subjects, including symplectic duality. And they form presumably a Shu category. And again, Justin and collaborators have been trying to figure out this Shu category in some examples. And even in the simplest sort of examples like these, you start getting perverse Schobers over C or complicated beasts. And I would love to see what this construction had to say about the chiral algebras. So in particular, if you consider this sort of sandwich picture, we put an holomorphic boundary condition on the right and a topological on the left, you get essentially an extension of the original chiral algebra. Because now you can have some of these modules that live at the end of a line, and you can have the line end also on the topological side, and then you get effectively a two-dimensional local operator. And so these are sort of analog modular extensions for rational conformal field theories. And so it would be nice to understand this better. Also, I'm curious to understand what the meaning of non-chiral slabs, situation where you have both holomorphic and anti-holomorphic vertex algebras combined in a modular invariant way, because this should give you modular invariants for these logarithmic CFTs. And I would like to see this. This seems to be an interesting topic. Let me now from now on. How much time do I have left? 5 minutes or?
Yeah,
I forget what the length was expected to be.
Yeah, about 10 minutes.
Okay. So I would like to hear some more concrete examples of this sort of questions, but it's a bit challenging, but let me try. So let me look at the theory of symplectic bosons. So just B-twisted free hypermultiplets. Why do they have conformal blocks? Right, and the action of symplectic bosons is the same as the action of free fermions pretty much, and free fermions don't have conformal blocks, right? And the point is that when you try to define the path integral for these symplectic bosons, there is no natural integration contour. So you had these holomorphic fields, Z, I don't know here, ZA or ZB, and they're just complex fields, and it's not quite clear which integration contour you should use to do a path integral. And so when you study correlation functions on symplectic bosons, you're doing an analytically continued path integral, on a contour path integral. And indeed, the B model for hypermultiplets literally is the theory which controls the integration contours for this path integral, if you use Witten's perspective on analytic continuation of path integrals. What could a non-chiral version of this theory be? Well, I can combine Z's and the complex conjugate fields, Z and Z bars. And then I could just integrate over a contour where Z is the conjugate to Z bar. This would be a fine natural contour and would give me an answer. Essentially, the original calculation was trying to compute 1 over square root of the determinant of the del bar operator. And the ambiguity in integration cycle was essentially the ambiguity in the choice of the square root. The non-chiral version is computing 1 over absolute value of the determinant of the del bar operator, and that seems fine. So there does seem to be a non-chiral version of the symplectic bosons. Okay. So could I use that to define a non-chiral version of the vertex algebras which occur for a general B model? So can I do a non-chiral version of the BRST reduction? So let me just remind you how the BRST reduction works. You take these symplectic bosons in representation N. You add fermions if you need. Those go on for a ride. Then you add ghosts, BC ghosts, which are valued in the Lie algebra. And you define a BRST charge, something which is schematically Cj plus BCC, where J is the Kasmody currents for G. This BRST charge has the property that when it acts on the B ghost, it gives you the current. So the current becomes exact, pretty much. And this gives, you take the cohomology of the BRST charge and you get something, you get a vertex algebra. This construction actually gives you a natural way to think about the modules, about conformal blocks for this vertex algebra. In the sense that you can try to build conformal blocks for the BRST reduction, starting from the modules on the space of bundles. But it is not clear to me if this sort of perspective would be subjective at all. So another wish. I wish I knew how to characterize fully conformal blocks for a BRST reduction of symplectic bosons in geometric terms that only involve maybe bundles on the Riemann surface or things like that. Now, learning from what as a string theorist, I became familiar very early on with constructions which allow me to define non-chiral versions of BRST reductions. So in string theory, you start with correlation functions of some CFT, which has a Virasoro symmetry, and then you add some ghosts and build the heuristic charge, which makes the stress tensor exact. And then in order to compute correlation functions in string theory, you integrate the correlation functions on the space of complex structures, the Riemann surface, with some ghost insertions to make a measure. And this is needed in order to get BRST closed, BRST invariant answers. Pretty much because the naive correlation functions you write are, have the property that the BRST variation of that is an exact form on the space of complex structures. And so you need to integrate things on the space of complex structures to get something that is BRST invariant. Similarly, you can write a formula for a correlation function of these gauge sympathetic bosons, which is an integral over the space of bundles, using bgauss to make a measure. This gives formally a single valued correlation function, single valued non-chiral correlation function for this vertex algebra. And I would love to know if this construction makes sense, if it's actually modular invariant, if it's computable. I worked out some very basic examples. Working genus, I find it very hard to work with band G on a Riemann surface of genus greater than 0. So all my calculations involved the insertion of modules and were done on the sphere. But I think this is an interesting construction that would be nice to understand better. So, and it has applications to in the context of analytic geometric Lagrange, which is about densities on band G, pretty much, and their properties. Now, if I don't think in the context of geometric Lagrange, a lot of applications involve Arakawa's VA. So I did calculations for this sort of things using in the context of Arakawa's VA for SL2, but I don't think I can discuss the details now. It's just to say that the constructions seem to make sense, it seems to have good properties, but it would be nice to have a general theory of it. And another thing I can mention, right, the other aspect, which is this conformal extensions of these vertex algebras seem to be also very interesting. And I'm trying to build some examples with Kertzing, but it's not, the process is not sufficiently advanced to give you an account for it. But it seems a fun question. Can you build modular and modular extensions of vertex algebras such, I don't know, SO8 at level -2 or PSU n/n at level 1 or the sort of vertex algebras which appear in these stories. Okay, I think I'm done. Are there any questions?
Let's all thank Davide. We'll do questions from the online audience first. Feel free to jump in. And any questions from the audience?
I have a question. So you said that you made the computations for Arakawa algebra for SL2, but you're talking about computation of what? I'm sorry.
So I computed non-chiral partition functions of Arakawa's array for the 4-puncture sphere on a 4-puncture sphere. So there are 2 spheres in the game.
The non-chiral?
Yes. And remembering. Sorry.
In what terms can you describe the result? I mean, you said when you say compute, it means that you can describe it in some terms.
Well, it's pretty much a bilinear of some elliptic functions. it's a, well, the way I present it is an integral of 1 over absolute value of a polynomial, degree 3 polynomial over the complex plane, or something like that.
And then somehow, can you match it with some gauge theory computation?
Well, what I can show is that this has the symmetries that the VOA has. So, this emerges in the context of a Suchu gauge theory with 4 flavors. This theory has a triality, which is only 2 strong coupling. So it has an oscillate global symmetry, but and it's expected to be triality invariant, but this is not manifest in the Lagrangian. It's not manifest in the presentation of the vertex algebra. So the vertex algebra is supposed to be a weighted level -2, but it's presented as as a gauged and a Suchu gauged sympathetic bosons valued in C16. So you take C16, you gauge, right, as C2 times C8. You gauge a C2, you get a VOA which has a swayed Moody currents, but it's far from clear that the VOA will be triadic invariant. What I did was to compute the partition, this non-chiral partition function of the VOA, and on a 4-puncture sphere, and verify that it is triadic invariant and also single valued.
Any other questions? Sorry, Sasha, are you?
Sorry, can I ask again? So I'm just blanking. So if I understand correctly, your example with Arakawa's SL2 VOA is supposed to confirm some statement you made earlier, right? So if yes, then what kind of statement you made earlier are you confirming by this calculation?
So I'm confirming. So I'm confirming that, first of all, I'm confirming that I can get a single valued correlation function for SO8 11 minus 2 times its chiral, anti-chiral partner on a 4-puncture sphere with some modules inserted, some vertex operators inserted. And furthermore, the answer I get also happens to have the symmetries that I expected the VOA to have, which is it's a nice check, although it's perhaps less striking.
And so you do it only for 4 punctures or for any number of punctures?
I only do it for 4 punctures.
Okay. And for higher genus? And for higher genus, can you do anything?
No, because I have no idea how to integrate over Bungie. But somebody who knows Bungie well enough might be able to. So you essentially try to integrate 1 over absolute value of the determinant of del bar for some representation over Bungie.
Everybody, to follow up on this, is this a calculation that could be done by putting the 4D theory on a 2-sphere times a surface and using any available localization techniques?
It should be, morally speaking, but I don't know how to actually do it. So I agree with you that this non-chiral 2D CFT should emerge from the 4D unequal 2D theory on a sphere. But in the practical details are not clear.
And any other questions locally or online? Let's think about it again. Wait, is there one? Anton? No, we're good. Let's thank Daphne again.